Hey, Stat 305, this is Will, and this video is to show you how to use JMP. Here's a tentative list of topics. First I'm going to show you a little thing or two about JMP spreadsheets, how to enter data and how to apply formulas to them to calculate some columns for using other columns of data. I'm going to show you how to make some plots, and I'm going to show you how to do various things in Chapter 4, which include fitting simple linear regression, polynomial regression, multiple regression models. I'm going to show you how to compute or how to find the correlations in R² in the outputs, do things with residuals, and make scatterplot matrices. Let's get right to it. So when you open JMP, it should give you a blank spreadsheet. The idea behind any of these spreadsheets to represent data is each column represents a variable and each row represents an observation. So I might enter a data set like this. I can say, well, here is, well, I'll just enter data without an example, just to show you how I do it. I can rename this column A just by clicking on it, and I can put some numbers in. That's a variable A. Here's a column for variable B. I just double-clicked on it. We have basically a data set now with 2 variables and 5 observations. And I can do more with these columns if I want. I can right-click and I can do a whole bunch of things with it. I can sort it. I can change the properties. Most useful, I think, is column info, though. Here you can rename it. You can, and the column properties menu is down here. It's important to make sure you have, for Chapter 4 at least, a numeric modeling type. There are numeric types, there are character types. For modeling types, they're continuous, ordinal, and nominal. You can check if you have the right data type by looking at this columns box. Everything should be numeric, continuous variable for now. Later at the end of the class we'll deal with discrete versions of this. But these need to be blue triangle icons. If I change this to nominal and hit apply, see B becomes this icon of a red histogram. I want that to be continuous. And you hit apply, it changes back to continuous. If you're having problems with finding parameter estimates when you do regression, that might be a problem. That might be one thing to check. I can create a new column. Let's say I want to create a variable. I just double-clicked here, over here, and that creates a new column. These dots denote empty cells. I can name it C, and suppose I want to sum A and B and put the corresponding entry in C. What I can do is I can calculate that with a formula, because I know there are only 5 observations here, but suppose there were 1,000 observations. You wouldn't want to go to every single cell and calculate, 1 plus 2 and then 2 plus 4 and so on by hand. There's a better way to do that, and if you're familiar with Excel, this is going to be natural to you. I can do that through this formula box. Now, before I work with this formula box, I want to show you how to access it. And you can do that in a couple different ways. I can right-click, I can go right to formula, or I can go to column info, column properties, and then formula here. Now, there's this formula box here. I don't know what it does. Well, it just shows you that it's stored a formula of some kind. You can click edit formula, and it comes up with the same box. Now, what I can do is I can say, well, I want column A, and I want to add it. I just press plus on my keyboard, and I click B, and there it is. And I hit apply, and all of your entries are filled that way. Now, that was a really simple formula. There are a bunch of more complicated formulas that you can do. They're built-in functions, grouped by field of math, I suppose. And you can, let's say I want to select statistical. You can compute column mean, standard deviation, sum, minimum, maximum, various quantiles, blah, 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 and you can include those in your formulas as well. I'm not going to go over the more complicated versions of that here, but needless to say, you can play around with this, and the time will come when you'll need to do this. I believe in Chapter 9, very end of the class, you'll find formulas useful for simultaneous confidence intervals. Whatever those mean, you're going to learn that eventually. Anyway, so that's a really simple spreadsheet. It has a formula. I think this plus is there because there's a formula. You can just double click on that to change it. And that tells you that there's a formula in column C. Alright, now I'm going to close out of this simple data set. Now I'm going to show you how to make a whole bunch of plots from Chapter 3. Histograms, stem and leaf plots, box plots, normal QQ plots, and scatter plots. And for that I'm going to use the New York Rivers data, which if I haven't already gone over it, I will go over it when I go over Chapter 4, and then I'll return again to it in Chapter 9. It's this data set where a few years ago 20 rivers in New York State were measured for nitrogen content, and the mean nitrogen content in milligrams per liter was recorded during the non-freezing seasons during the spring, summer, and fall months. And the nitrogen content we take to be a measure of pollution. And we want to try to predict pollution based on what we're doing with the surrounding land. Now there's X1, which is how much land we're using in agriculture, X2 is forested, X3 is residential, and X4 is, well, sorry, I think I said that wrong. X1 is agriculture, X2 is forested, X3 is residential, and X4 is commercial industrial. Each of those are the percentage of land that is being used for that respective purpose. Alright, I'm going to open that data set. That's going to be rivers. This data should be available online. Alright, so I have a column with the river name. That's, by the way, if I want to check what type that is, I go to column info, I right click that, I right click the column, go to column info, and it's character and it's a nominal variable, so it has this red histogram next to it. I want all of my other variables to be numerical and continuous. I have my x1, x2, x3, x4, and y. I'm interested in y. I'm interested in the pollution of the rivers first and foremost. So what I'm going to do is I'm going to check the distribution of that data. I'm going to go to Analyze, this top menu. I'm going to go to Distribution. And I'm going to select Y. I'm going to make sure Y is highlighted, and I'm going to select Y columns. And that puts it into this box. Now, JMP is going to run some commands on all the variables that are in this box. I click OK, and here's your standard output. You've got your plots, you've got your quantiles, you've got your summary statistics, and you can add more summary statistics by clicking this red triangle and going to customize summary statistics. You have a whole bunch of different things. Be careful with the interquartile range, because JMP will probably compute the interquartile range differently than what you're going to need to do in your homework. So just be aware of that. By the way, these red triangles in the output windows, they are always drop-down menus. And if you're at a loss for what to do sometimes, just play around with the red triangles. For more plots, I can go to this red triangle. I can add a quantile plot, a quantile box plot, which is different than an outlier box plot for some reason, but they're both very similar. Most of your box plots you're going to want to compute by hand in Chapter 3, because you're going to want to show where the various features of the box plot are. I can compute a stem and leaf plot by going to, that was really fast, I'm sorry. I can go to the red triangle under Y. I click stem and leaf plot, and that should be checked. That will be checked once I click on it the first time. And you get the stem and leaf plot, and there's this relationship between all the plots that I have and the data, because I can highlight a bunch of points, and those points will be emboldened in the stem and leaf plot. And they'll also be emboldened in histogram. So if I highlight different points in the histogram will be highlighted. Now, I don't like how this histogram is aligned. I don't like this vertical histogram business. What I can do is I can go to this red triangle. I can go to histogram options. I can uncheck vertical, and there it is, horizontal now, same as the box plot. I can go to normal quantile plot if I want a normal QQ plot or normal probability plot, all names for the same thing. Now if the points are kind of fading, what you can do is you can highlight all the points, because remember the highlighted points get emboldened, emphasized in your plots. It makes the points darker. I can change the point size by right-clicking in the plot window. I can go to row, what can I go to? Marker size, and I can go to medium, let's say, and it makes the points bigger and far easier to see. Now, remember, normal QQ plot is a way to check if your data are bell-shaped, and if the points in your normal QQ plot lie in a straight line, your data is bell-shaped, otherwise it's not. So these points are not in a straight line, so you do not have normally distributed data or bell-shaped data. And that's useful for knowing, for reasons which will become clear in Chapter 6. Now, did I forget any plots? And I think that's it for plots. Let's see, histograms, stem and leaf plots, box plots, normal QQ plots, scatter plots. That's my other plot. For scatter plots, what I can do is I don't do analyze distribution, because that only takes one variable at a time. What I should do now is I should, let's say I want to plot y against percent of forested land, x2. What I do is I go to analyze, I go to fit y by x. I put y in a response, I highlight x2, click x factor, and I hit OK. And that generates a new output window with new options in your menu bars, and this gives you a scatter plot. I want to make the points bigger so I can see them a little bit more easily. What I did, if that was fast for you, I go to marker, I right-click the window, go to marker size, and I click medium. And this is what the scatter plot looks like of y and x2. Now, what I can do also is, well, let's check out the options. For simple linear regression of y and x2, I have a bunch of tools, and for polynomial regression as well. So now I'm going to transition from these plotting things to fitting simple linear regression and polynomial regression. What I can do is to fit, for simple linear regression, to fit a line of y and x2, I just go to this red triangle, and red triangles are always menus in JMP, by the way, and I click fit line. And when I click fit line, it'll give me a whole bunch of output, an equation for the line, it'll plot the line, it'll give me the r squared for the line. This is your r square, your coefficient of determination. There's this thing called an adjusted r square that's beyond the scope of this class. It gives you the mean response. Root mean squared error we're not going to talk about for a while. We have 20 observations in our data set. We have 20 rivers. That's what this number is right here. Lack of fit you don't need to know about. That's beyond this class. Analysis of variance we're not going to get until Chapter 9 and later Chapter 7. Parameter estimates are what you want to focus on besides the r square. So the intercept is this 2.35 That's your beta 0, that's your B0 in your model. Remember, you have the model, or a fitted model, y equals b0 plus b1x. So b0 is going to be your intercept, and your b1, if x2 is your x in this equation, b1 is going to be your slope. So your slope on x1 is this thing, this estimate under x2. Your intercept is going to be this estimate under, well, intercept. This standard error t ratio and probability value we're not going to touch until chapter 6, so don't worry about them just yet. Just focus on the r square and the estimates. Now, this linear fit gives you a bunch of options, a bunch of useful options. Suppose I want to check residual plots. Suppose I want, because we talked about plotting residuals to check model validity. So what I can do is I can go to this red triangle and I can click Save Residuals, and what that does is it saves, well, does what it says it will. It'll save your residuals in that column. I can do a similar thing for predicted values, for fitted values if I want. And fitted values are values that I take by going to each data point, dropping down to the line, and evaluating y. So for that, if I want, I can go to the same menu and click Save Predicteds. And those are all your values at all the points in x2 that you observe, but evaluated at the line. So if I wanted to have the fitted value for this point, which is Fishkill River, there is an actual Fishkill River. To compute the fitted value, what I do is I'd go here, I'd drop down, I'd go to the line, I'd drop over, and I would go to the y. And that's exactly what's here. I find this is about 1.25 or 1.2 by my estimate, and the number 1.21 is actually computed as that fitted value. So that's fitted values. Now remember, residuals are the differences between those fitted values and the actual points. Well, I got that the other way around. Residuals are the differences between the observed points and the fitted values. So if I wanted to compute that residual, I would take the y here, which is a little over 2, and the fitted value, which is about 1.2, and I would get, for Fishkill River, that residual is 0.83. So that's fitted values or predicted values and residuals. So, and I can plot those if I want by doing a fit y by x of residuals on predicted values or residuals on x2. What I can do now, though, quicker, is I can go to this menu and I can click Plot Residuals. Now this is useful. So it plots the residuals, or y actual, y predicted. That's, oh, here we go. Residuals on predicted values, that's useful. Residuals on row number, that's also useful. And it gives you a normal quantile plot of the residuals. I tried not to ask you to actually compute normal quantile plots of the residuals in your homework, but just in case I forgot, this is how you do it, and this is where you find it. To make these plots bigger, you can click and drag the plot window. I believe you can do that. Yeah, it's kind of unwieldy, but you just click the plot window and drag it, and it opens up here. Now, there's really no pattern, up and down pattern of the residuals about the predicted values, so that doesn't cause alarm. What I'm concerned about is, well, is if these 2 points above and below here part of the pattern, we see this sort of fanning out in the variability of residuals about the y equals 0 line, and that's that's indicative of a non-constant variance of y with respect to x2, and that may be a problem. Or what I could do is I could say, wait a minute, these 2 points are just outliers, and if we ignore those points, the variability seems approximately constant. I guess you could argue either way. There's so few points, it's kind of hard to tell, though. 20 points is not a lot. For the normal quantile plot, remember if the residuals are, if the points in this normal quantile plot are in a straight line, the residuals are normally distributed, otherwise not. The points look to be in a straight line, so residuals are normally distributed. That's a good thing. Great, that was residuals and scatter plots. What else am I doing here? I've also covered simple linear regression. Now what I can do is I can do polynomial regression. And for that, I'm going to close out of this, because the linear fit is pretty good here. Let me show you something that's not actually a good linear fit. I'm going to go to Analyze, Fit Y by X. I'm going to pick Y. By the way, if I wanted to do residual plots by hand, I could just click either of these, put them in the Y, click the other one, put them in the X. I'm going to regress, or I'm going to plot, not regress yet, I'm going to plot Y on X1, the percentage of surrounding agricultural land. Now, that actually looks pretty good, pretty linear, I mean, not good with respect to some other things, but that wasn't the one I wanted. What I do want, now that I can remember, is I want Y on X3. There we go. And X3 was, let me see what it was. Oh yeah, residential land. There's a lot of residential land around Hackensack. That's called an influential point, an outlier in the X direction. Beware of those, because they'll influence your line. They will bend it out of proportion more than your other points, oftentimes. There may, I can't really decide whether to fit, a line here, or if I want to fit a polynomial that kind of curves around this way. But, I could fit a line. Just for the sake of demonstration, I'm going to fit a polynomial that'll hopefully do something like this. The thing to do, and I know this is kind of, a tricky data set. Do I trust the line here and ignore this point, or do I acknowledge this point as part of the overall pattern and fit something that's like that? The answer is, in practice, do both. Analyze your data with and without this outlier, and think really hard about how the data was taken and whether or not, and what this point means, and whether or not we can exclude it. I'm going to keep this point, and I'm going to fit a polynomial to it. And how I'm going to fit a polynomial to it is I'm going to do this. I'm going to go to the red triangle. I'm not going to go to fit polynomial. That does something that I don't want. I'm going to go to fit special. Fit polynomial does fit a polynomial, but it doesn't give you the estimates of your parameters directly. It gives you something that you'll have to, centered polynomial that you'll have to transform. If I go to fit special, then I can do something different. So I select no transformation. I don't constrain the intercept or the slope. I uncheck centered polynomial. So the default in fit polynomial was to center your polynomial. That's what you don't want. So you uncheck this box, and I select the degree that I want. Let's say I want to fit a cubic polynomial of that data set. That's what I click under degree, and I hit OK. And this, maybe a cubic fit wasn't such a good idea. I don't know if it does that. That predicts negative nitrogen content eventually around here. So it's not really useful for interpolating. So what I'm going to do is I'm going to remove fit. I'm going to go to this red triangle, remove fit. I didn't like that at all. I'm going to go to fit special, uncheck centered. I'm going to go to degree 2. Let's see if this is any better. Ah, not good either. Predicts really high pollution values. So I'm going to remove that fit 2. I'm going to go to fit special again. Let's say degree 4. That's also terrible. But I'm going to stay with this one, just for the sake of staying with something. I could probably do this all day and come up with really bad results. What I wanted was a curve that kind of just went like that. But maybe that's not the natural behavior of the data, and I'm just reading into things. In any case, the model that I've just fit, polynomial for degree 4, looks like this. It's of the form y equals b0 plus b1 x plus b2 x squared plus b3 x cubed plus b4 x4 x to the 4th, sorry. And so this is what b0, b1, b2, b3, b4 mean. And just looking at that and looking at the output, I say, well, this is my b0, this is my b1, b2, b3, and b4. I've got my r square of the fit here, it's 0.74. And my parameter estimates are nicely listed down here, if I forget what they are. So they're both here in this fitted equation, and down here under estimate. And just to show you what happens when I do fit polynomial, I can go to, let's say, fit polynomial degree 6. It gives you this centered polynomial here. I don't like this x3 minus something, because then I have to expand this out and simplify in order to get the actual parameter estimates in this form. And that's a headache and just a whole lot more trouble than it's worth. So don't do that. Go to fit special for polynomial regression. Alright, now, what's next? Multiple regression. For that, I go to Analyze, Fit Model. So if I were to, because I'm now going to regress on multiple columns. In fact, I'm going to say I'm regressing on x2 and x3, which are percent forested land and percent residential land. So for analyze, just to recap, analyze distribution was to analyze the distribution of one variable, one list of numbers. Fit y by x was to plot one variable against one other variable. But what if I want to assess the relationship between one variable and multiple covariates? That's when I go to Analyze Fit Model. Now what I do is I can say I want my y, I highlight y, click y to be here, and then for my main effects I can highlight x2, click add. That's one variable I'm regressing on, and then x3 and add that too. So I'm regressing y on x2 and x3. And then I click run. And it gives you a whole bunch of other stuff. Don't pay attention to leverage plots. This is your actual values on predicted values. And that can be useful, actually. So your y-hats, remember, are if I were to take this fitted line and plug in, sorry, different fit line. Let's say B1, X1, because this is multiple regression now. I have a different model. Y equals B0 plus B1, X1 plus B1, X2, and so on. Well, actually, but I'm not using all the variables. I'm just using X2 and X3. So my model would look like this. Y equals B0 plus B2, X2 plus B3, X3. That's my fitted equation. Now this is an equation for a plane. And what I want to do to get, and there's variation about that plane, and what I want to do to get those fitted values is to estimate these things, B0, B2, and B3. That's going to be under these estimates. Here's B0, here's B2, here's B3. And what I can do is I can plug in, let's say, an X2 in the data, an X3, and that'll predict the value of Y on the plane. And that's what those predicted values are. I can take the R-square value, that's 0.64, and the square root of that value is actually going to be the correlation between the actual values and the predicted values. That's the correlation you want to pay attention to most of the time. So you got, anyway, you also, this output also gives you residual plots, residuals by predicted values. Let's see what's available here. If I want to save columns, I can go to this red triangle under Save Columns. I can save residuals. I can save different kind of residual called studentized residual, which we won't get to until later. I can save predicted values. I can save a whole bunch of stuff under Save Columns. Now, I don't think it gives you a normal QQ plot of the residuals, but you'll just have to save the residuals and then go to fit Y by X to plot. Go to fit distribution. Analyze distribution to get a normal QQ plot of the residuals once you've saved them to your spreadsheet. All right, moving right along. So I've done simple linear regression, polynomial. I just did multiple regression. You know how to compute R and R squared, or you know how to get R squared, and correlation R is just the correlation between the residual and fitted values is just the square root of that R squared that you find. Now, I showed you how to print residuals and fitted values and plot those. Scatter plot matrices. So the trouble with multiple regression is that there's no, scatter plot where you can see all the data all at once, because you're plotting Y against X1, and X2, and X3, and X4. Well, what scatter plot do you use? The answer is all of them. So what I can do is I can go to Analyze. We've done distribution. We've done fit Y by X. Don't do match pairs. We've done fit model. What I'm going to do for those scatter plots of Y against all of the covariates is go to multivariate methods, and then I click multivariate. And what I can do is I can select all of these columns. I'm going to highlight them all of my original columns that are numeric and continuous. And I click Y columns. And for all these 5 variables, it's going to make a scatter plot of each variable on each other variable. So for example, here's a scatter plot of X3 on X4. Here's a scatter plot of X4 on Y. And here's a plot of Y on X4. Now those are your scatter plot matrices. And that's useful for telling whether two variables, for not only seeing how Y varies individually with each covariate, it's also useful for assessing how correlated the covariates are, and that's really important in practice. If the variables are correlated, then when you do statistical inference, which we'll get to in Chapter 6, correlation between and among covariates messes things up. And there are various ways to deal with that, but that's beyond the scope of this class. Anyway, you'll see things like, well, x1 and x2 are highly correlated. Now, there's this matrix of correlations, which gives you the R value, the correlation between each variable and each other variable. So, for example, the correlation between x1 and x2 is minus 0.68. That's a fairly strong negative linear relationship. The highest correlation, I think, is between x3 and x4. That's 0.85991. That's a strong positive linear relationship. But that may be stronger than we would otherwise expect by looking at the data, because you see there's this one point out here, and the correlation, the line's going to, that point, since it's all the way out here, that line is going to go wherever this point goes. That point has, single-handedly has far too much control over where that line goes. And that could be one of the reasons why the correlation is going to be high. Nevertheless, that's what we expect, because x3 is residential land, x4 is industrial land, and that both are just measures of how generally developed that area is. So we expect the correlation between those two to be high. Anyway, that was done by analyze, multivariate methods, multivariate. And this is the output it gives you by default. And there are various options for the scatter plot. Matrices show points, that's what you want. I can take away these annoying red lines by just unchecking the density ellipses. There's all this fancy stuff that, in my opinion, just ends up looking unprofessional. Anyway, it's still a pretty nifty thing for quick and dirty analyses. There are a lot of options on this red triangle. I don't think you need any of these. Let's see what ellipsoid 3D plot does. I've never actually done that. Let's see. So I'm making a 3D ellipsoid of x1, x2, and x3. Whoa! I didn't know this existed. So this is pretty neat. So you can remove the whole problem of, what do you do when you have three variables and you want to picture the data like you would in a 2D scatter plot. If I just go to multivariate methods, ellipsoid 3D plot, I take back what I said about graphics in this program. But anyway, you can get something like this, where you can just move around and by clicking and dragging, and you can see what the data look like. And you can see it's kind of disc-shaped. The really high correlation between x1 and x2 at every level of x3, but not really much else. Well, except the ellipsoid is kind of disc-shaped because of this outlier out here. And the culprit is, let me see if it'll tell me what the culprit is. Nah, I'm just playing around, I should stop. Anyway, so that's jump, and you now know enough to branch out on your own and use jump for homework assignments, and that should be it.